Chapter 13 deals with the rate of a chemical reaction and deals with the common term known as chemical kinetics. And kinetics is just a fancy word for how fast a reaction is going. So a reaction can go at the pace of maybe a sprinter. It can go as slow as a turtle, and it can go at an intermediate speed, such as a car traveling from point A to point B. And you can have reactions that occur at a supersonic rate, something that's extraordinarily fast. In all cases, what we're actually doing is we're measuring the change in concentration of reactant over time. We're also measuring the change in the product over time. Now, big difference here between reactant and product. We would expect the reactant to decrease over time and the product to increase over time. So just take a look at this very simple chemical reaction of A going to B. A is my reactant, B is my product. We imagine and visualize a situation that over time, the concentration of A is going to decrease, and simultaneous to that, the concentration of B is going to increase. So chemical kinetics deals with how fast a reaction is going to proceed. This idea of rates is akin to the idea of velocity. So if you drive your car and come to school, maybe you're going at 20 miles per hour on the highway or on the local roads, or 40 miles or 50 miles per hour on the highway. Same thing here with chemical kinetics. It's a velocity, and we measure velocity as the change in concentration over time. So a standard unit would be some concentration that gets turned over over time. In other words, if we're measuring the concentration of reactant, we would measure the concentration of that reactant that decreases over some unit of time. It could be seconds, it could be minutes, it could be hours. And the concentration may not be in molar, it could be in millimolar, micromolar, nanomolar, etc. Likewise, if we're measuring the appearance of product over time, we're measuring the appearance of the product millimolar or nanomolar or micromolar or molar over time. In this case, the time doesn't necessarily have to be in seconds, but it could be in hours or days or what have you. So the idea of concentration over time is known as a rate. Rate is kind of like miles per hour on your car, how fast the reaction is going to proceed. In this case, it's concentration over time. Now, coming back to this A going to B, this is the most simplistic reaction. The rate, or how fast that reaction is going to proceed, is dependent on two things. It's dependent on the concentration of A, and if you have more A reactant that you start off with, then you will produce more B product. Likewise, if you start off with less of the concentration of A, you'll start off with less product of B at the end of the reaction. So the reaction rate is not only dependent upon the initial concentration of A for this reaction A goes to B, but it's also dependent on another thing, and that is the order of the reaction. So this is an exponent here, and the order of the reaction determines the rate of decay of A. This A can decay with zero order kinetics, it can decay with first order kinetics, it can decay with second order kinetics. So that's the reaction order. The order of the reaction is always determined experimentally. And then finally, not only is the order of the reaction important, but this proportionality constant K. That is a rate constant. So if I'm going to write this again, the rate of A going to B is going to equal to the proportionality constant K times how much of A we started off with, and that concentration of A is raised to the power of X, so-called the order of the reaction. Remember, this order is going to be either zero order, first order, or second order. And in this case, the rate of this reaction is going to be some proportionality constant K times the initial concentration that you start off with of A, and that is raised to the power of the order of the reaction with respect to the reactant A times the concentration of B, and the order of the reaction with respect to the concentration of B. So the overall order of this reaction is just going to be x plus y. And the rate of the reaction is also determined by how much B you start off with. That determines how much C and D product you get. You have to multiply it by this proportionality rate constant. That is something we have to find. That rate constant has different units depending upon the order of the reaction. So as stated before, thermodynamics really deals with a reaction, whether it's going to take place or not. That's going to be studied later in this course, whether a reaction is spontaneous or non-spontaneous, or if the reaction has free energy that favors the formation of products. That's later in this course. This chapter is dealing with rates and how fast the reaction is going to proceed. Let's take a look at this again. This is a more simplistic view without looking into the order of the reaction. A is going to be the rate of change of the concentration of A over time is going to be negative. And the rate of change of B, the change in concentration of B over time is going to be positive. So for those of you that have calculus training, this is the derivative of A with respect to t, time. And so that's decreasing. And this is the derivative of B with respect to t time. So the rate of change is nothing more than the first derivative. For the reactant, that rate of change is going to decrease because the reactant is decreasing over time. And for the product B, it's going to increase because the product B is going to increase over time. Because kinetics deals with time, you can look at a reaction and A is going to decrease over time, B is going to increase over time. Here is our time scale. And I want to again emphasize, though this may be a repeat, A is going to decrease with some type of order. First order, second order, or zero order. And that is what we're trying to deal with here. Okay, one of the goals of this chapter is trying to figure out not only your proportionality constant K, but also the order of a reaction, this exponent X. First things that we have to deal with in this chapter in figuring out the rate is this proportionality constant K, as well as this exponent X, the order of the reaction. A lot of times the rate of the reaction is determined by the coefficients of the balanced chemical equation. So if you look at this reaction, hydrogen peroxide decaying to water and oxygen, I can just tell you right now that's a reaction that's going to be very, very slow. Just imagine buying hydrogen peroxide from Walmart and letting it sit there. You don't really see it by the end of the day. Water and oxygen gas. So this reaction is going to go slow, but it does happen. And if we want to determine how well it happens or how fast it happens, we are interested in the rate. So if you look at this reactant, there's 2 moles of hydrogen peroxide. The rate expression actually has to do with the inverse of that stoichiometric coefficient. So minus 1/2 the rate of change of hydrogen peroxide over time must equal to 1/2 the appearance or the buildup of water over time plus the rate of appearance of oxygen over time. Notice that we're talking about concentration. So that bracket implies concentration. Usually it's moles per liter, but it can be in other types of units as well, like millimolar or micromolar or picomolar. So, but it's a moles over liters. So notice the relationship between the stoichiometric relationship. Now, oxygen is a gas, so a lot of times people can convert that oxygen gas into pressure. Or you can convert that pressure into concentration using PV equals nRT. And so anytime you see a gas in your balanced chemical equation and you want to figure out the rate, you can go from the concentration of oxygen, or you can go for the pressure of oxygen. P will equal to nRT over V. So just be aware that oxygen can be expressed both ways. It can be expressed as a concentration, in this case moles per liter, or it can be expressed as a pressure. And when it's expressed as a pressure, it's usually expressed as atmospheres or millimeters of mercury or torr or some appropriate unit of pressure. So if we're going to look at some practice problems, the rate expression for the following reaction: methane undergoing combustion to form CO2 and water. It's a balanced chemical reaction. So the rate expression for this is going to be The rate of formation of H2 gas per the problem is 0.078 molarity per second. So going by our equation here, this will decrease by 1/4 the pressure of pH3 over time. It's going to increase by the pressure of P4 gas over time plus 1/6 the pressure of H2 gas. Know that this value here is going to be 0.078 molar per second. That's for 1 mole, but we have 6 moles. This is going to increase at 1/6 the rate. And we want to figure out the rate of these two guys. So the change in pressure, the disappearance of pH3, we will call that minus 1/4 x. And that's going to decay at a rate of the appearance of P4, which is going to be x, plus 1/6 of this, which is 0.078 molar per second. So let's solve for x here. That will give us the rate of disappearance of the pH3 over time, which coincides with the rate of appearance of white phosphorus P4 over time. Of course, this is going to diminish at 1/4 the rate because of this being 4 moles that are decaying, giving rise to 1 mole of this and 6 moles of that. So I'm going to just do minus x over 4 is going to equal to x plus 1/6 times 0.078. I'll do that arithmetic. 0.078 divided by 6. 0.013 x plus 0.013 must equal to minus 1/4 x. So in this particular situation, I will just multiply by 4 to get minus x equals 4x plus 0.013 times 4, 0.052. And now I'll just solve for x. I'll move x to this side of the equation and get 5x. And that's going to equal to minus 0.052. X is going to equal to minus 0.052 divided by 5. And doing that calculator, I get an answer 0.0104 as my value of x. Back to this problem here, the rate of change of pressure for pH3 is going to be the pressure of pH3 over time is going to equal to minus 1/4 0.0104, which is going to equal to 6 times 10 to the minus 3, or 0.0026 molars. Now, even though this is pressure, the concentration units were stated in the problem, so technically this is a change in concentration over time, not the change in pressure. But just realize that when you're dealing with gases, you can go from pressure to concentration. And the appearance of the change in concentration, or pressure P4 over time, is simply equal x, which is going to be 0.0104 molar. Rate of appearance, now notice this is a positive sign because it's a positive sign because it's the rate of appearance of this, and this has to be a negative sign because it's the rate of disappearance of this. And then finally, the rate of appearance of hydrogen gas be 1/6 of our 0.078, and by 6, 78 divided by 6 is 0.013 molar, excuse me. This is a very important part now of this course, dealing with the reactant A going to product B. So remember, the rate law is going to be rate is equal to a proportionality constant K times the concentration of A over this exponent that we have to experimentally determine. So this exponent X is the order of the reaction. So the order can be 0 order, it can be first order. The reaction X, this exponent here, is what we're going to focus on. The reaction X, or excuse me, the decrease in concentration of A over time can be 0 order. In this case, the rate law, or the change in concentration of A over the change in concentration over time, is just a rate constant K. X, experimentally determined, is 1. That means A decreases with first order kinetics. That is, the rate of change of reactant A over time is K times the concentration of A. That means if you double the concentration of A, that is, the reaction rate is also going to double. If you triple the concentration of A, the reaction rate will triple. If x is equal to 2 for the reaction A going to B, that exponent is 2, then the reactant A will increase over time with second order kinetics. So the rate law, or the rate of change of concentration A over time, this reactant, is equal to rate of proportionality constant K times the concentration of A squared. That is, if you double the concentration of A, the reaction rate will go 4 times as fast. If you triple the concentration of A, initial reactant A, the reaction rate will go 9 times as fast. If you quadruple the initial reactant A, the reaction rate is going to go 16 times as fast. Notice here the concentration over time. The concentration over time here is linear, which is zero order reaction. So really it's independent of the initial starting material. Notice your rate law has no concentration of A expression here. If your x is 1, the concentration over time is a descending curve, so A is going to decrease over time. Also, if your x calculated is 2, then that also concentration over time is going to decrease. So when you experimentally determine this, are you going to have either first order decay kinetics for A or second order rate kinetics for A? So that's when you have to do a linear transformation. So the linear transformation is actually shown here. Transformation, if you plot the natural log of the initial concentration A time, the slope is a straight line. So that's a linear transformation, and your slope is your proportionality constant, rate constant K. That's a first order. Now if you plot 1 over concentration over time and you get a straight line whose slope is increasing, and that slope is your proportionality constant K, then you have a second order reaction. So in order to determine whether you have either zero order, well, it's a straight line straight up concentration over time, but to discriminate between first order and second order, you're really going to have to plot the natural log of your initial concentration over time. See if it's a straight line. If it is, then A decays with first order kinetics. If that doesn't work, then you're going to have to plot 1 over concentration over time and look to see if you got a straight line. If you do that, that means the straight line for this curve, 1 over concentration over time, is second order kinetics. That means the concentration of A decays in a second order manner. So both of these, if I were to zoom out, going to this represents a linear transformation, and this going to this represents a linear transformation. The net effect is, if you want to determine whether A, your reactant, in the reaction A going to B is going to decay at what rate, the first order decay is going to be this, the second order decay is going to be this. A is going to disintegrate according to the natural log of its starting material, starting concentration. A for second order decay is going to decrease according to 1 over the concentration, or the reciprocal of the starting amount. Notice the integrated rate law here. So these are very important, so I recommend that you bring this sheet to the exam, and you can determine the concentration of A at some time t, provided you know the initial concentration. You can determine the concentration A at some time t, provided you know the initial concentration. These two are equivalent if you just by the natural log, so that's a first order decay. And then finally you can figure out the concentration at some time t, provided you know the initial concentration. All of these reactions are specific, all of these equations are specific for zero order, first order, and second order, and they are a good consultation tool for you to use on the exam. Obviously we need to know the rate constant. Another thing I want to bring your attention to is over here. For zero order reaction rate, whether you double A or triple A or quadruple A, the reaction rate stays the same. For a first order reaction, if you double the concentration, the reaction doubles. You triple the concentration, the reaction rate triples. Quadruple the concentration, your starting material, the reaction rate quadruples. In a second order decay of A going to B, as you double A before, the reaction rate squares. If we triple it, the reaction rate squares to 9. We also have another thing here called the half-life. the time required to get 50% disintegration of A, your starting material. So notice for a first zero-order reaction, your half-life is determined by your initial starting concentration. What's really strange is for a first-order decay, your half-life, or the time it takes to get 50% of your concentration, is actually independent of your starting concentration. So whether I start off with a lot of A, as A goes to B, or very little of A goes to B, the half-life is still going to be the natural log of 2 over the rate constant. The half-life for a second-order reaction is based on the reciprocal. Another very important point here that you must realize is the units. The units of K are going to differ. So rate equals K, times the initial concentration of A raised to its order, whether it's 0, 1, or 2. If it's 0, then the rate law units of K are going to be molar per second. If the rate is going to be this, then the rate law is going to be that units of K is going to be 1 over second. And then finally, if your rate law is this, that proportionality constant are going to be 1 over molar times 1 over second. This practice problem here, the reaction 2A goes to B is first order with respect to A, with a rate constant of 2.8 times 10 seconds to the minus 1 at 80 degrees C. How long will it take for A to decrease from 0.88 molar to 0.14 molar? Well, two things here. The rate law is first order with respect to A. So the rate law here is rate equals K times the concentration of A. The rate law, because it tells us that the decay of A is first order with respect to A. So that concentration of A, or that exponent here, is 1. And we are given a rate constant. We're also given a temperature, though the temperature does play a role in how fast the reaction occurs, but we won't need it for our equation here. All we need to do is consult this table. We know it's a first order with respect to A, so the equation that we will use here is, well, we can use both of these equations are equivalent, but we'll use natural log at A equals natural log of the initial concentration minus KT. The T here is time, not temperature. The T here is time. Okay, time. The natural log of the initial concentration. So we have the natural log of A at some time T is going to equal to the natural log of the initial concentration minus KT. And then the time is what we're trying to solve for. The initial concentration is this. It's a decay, so we're going initially from molar to 0.14 molar. Remember, A has to decrease over time, and it's decreasing with first order kinetics. Minus sign here, minus 28 time t. So putting that in my calculator, I get an answer of 0.065. And put another digit here, 0.0657, and my units are going to be seconds. 0.0657 seconds, I disintegrate from 0.88 molar of A to 0.14 molar of A, because the reaction is first order with respect to A. Determining the rate law and the overall rate of a reaction for a reaction that you're going to perform in the lab, S2O8 reacting with the iodide anion, and this reaction is going to be done in the lab. You're going to notice a color change, or the color disappearance. And how will we determine the rate law? So look at this reaction here again. Law is going to be the rate is going to equal to reaction proportionality constant K times S2O8 minus 2. That's going to be raised to its order of decay. I'll just call that A, times the concentration of I minus, and that's going to be raised to its order B, the exponent B. So we have to determine this experimentally, and was to get the rate law as well as the proportionality constant K. So if we're able to successfully get the orders A and B and the rate constant K, then we can be able to determine how fast the reaction would go under any concentration of this thiosulfate ion and under any concentration of this I minus ion. So this is the data table that we are given. And the first thing you want to do is look at this data table and see what reactions we want to compare, or what experiments we want to compare. I'll compare experiment 1 and experiment 2. Let's draw or write out our rate law. Rate 1 of 2 is equal to, our rate law is K, sulfate anion raised to its exponent A, times the anion raised to the exponent B, that divided by rate 2, which is K, times S2O8 minus, that's raised to the order A, minus, which is also raised to exponent A. These values in, rate to K, and for experiment 1, the rate was determined to be 2.2 times 10 to the minus 4. 1. 2, that experiment 2 under these concentrations had a rate of 1.1 times 10 to the minus 4. Notice the units molar per second. Equals to the constant K. Let's look at experiment 1 here as we calculate these ratios. The concentration of S2O8 minus 2 is 0.080 molar to its order A. For experiment 1, its I minus is the concentration point of 0.034 to order B. And now let's look at rate 2 from experiment 2. We already know that experiment 2 has a rate of 1.1 times 10 to the minus 4. The S2O8 minus 2 concentration for experiment 2 is 0.080 molar. That's raised to the order A. And I minus for experiment 2 is 0.017. For experiment B, or that is raised to order B. So the K's cancel. This and this cancel out. So you are left with 2.2 times 10 to the minus 4 divided by 1.1 times 10 to the minus 4 is going to equal to 0.034. That divided by B divided to the power of B divided by 0.017, that to the power of B. I can group my powers together. 2.2 times 10 to the minus 4 divided by 1.1 times 10 to the minus 4, that's actually 0.5, which is 1/2. 0.034 divided by 0.017, that's also 1/2. And I could group this under the whole exponent B. The order of the reactant I minus, first order kinetics, because B is equal to 1. So now I figured out the order of decay for I minus in this reaction. That is going to be I minus decays with first order kinetics. Figure out the rate of decay of S2O8 minus 2, that reactant. So in order to do that, I will compare experiment 2 and experiment 3. So let's compare experiment 2 with experiment 3. Experiment 2 with experiment 3, 2 over the rate of 3, K times the concentration of S2O8 minus 2 raised to the order of its decay, the I minus raised to the order of its decay, but we already know it's 1 because we solved that previously. And that ratio has to equal to the rate law of experiment 3, which is also S2O8 minus 2, that raised to the order A, and I minus, which we know from previous comparison of their data tables, has an order of 1. So rate 2, we know from this reaction, is 0.080, and its reactant experiment 2, the concentration of S2O8 minus 2 is 0.080. The concentration of I minus is 0.017. Its rate is 1.1 times 10 to the minus 4. Rate of 2.2 times 10 to the minus 4, and these are the concentrations of those reactants that gave you this rate. K's and K's cancel. The 0.017 to the power of 1 cancels with the 0.017 to the power of 1, and we are left with 1.1 times 10 to the minus 4 divided by 2.2 times 10 to the minus 4. That is also equal to 1/2. 0.080 divided by 0.0160. Both of those are raised to the power of a, so I'll just group them together. 8 divided by 0.16 actually is also 1/2. So 1/2 is equal to 1/2. So here A is also equal to 1. The decay of the reactant S2O8 minus 2, the thiosulfate anion, decays with first order kinetics. So going back to our rate law here, complete version of the rate law. Our complete version of the rate law is going to be rate is equal to K times, the rate law is going to be rate is equal to K times S2O8 minus 2 raised to the first power and I minus raised to the first power. Now how do we get K? K by either plugging in any of these experiments, the concentrations to this rate law. So I'll just pick, maybe let's just pick the third experiment. You can also pick the first or second, it really doesn't matter. And whichever one you pick, you're going to solve for K, and that will be the rate constant K. Make sure you get the proper units. It's incredibly crucial that you get the proper units for this. So K, we get rate is equal to K times the concentration of S2O8 minus 2, that's raised to the first power, and I minus to the power of 1 raised to the first power. The overall order of A is 1. The overall order of B is 1. So S2O8 minus 2 decays with first order kinetics. I minus decays with first order kinetics. So all the equations for first order rate law apply for both these reactants. By the way, the overall order of this reaction is 1 plus 1, or A plus B, and that's going to equal 2. So the overall order of this reaction is 2. Solve for our rate law. So K, let's choose experiment 3, but we can choose experiment 1 or 2. It's going to be the exact same answer. Experiment 3 was 2.2 times 10 to the minus 4 is equal to K times the concentration for experiment 3 that gave us this rate of, by the way, our units are molarity over second. Here it's going to be 0.160 molar. Those are the units raised to the power of 1 times 0.017 molar. That's also raised to the power of 1. So our units here, m times m is moles squared or molar squared. And so let's solve for K here. Okay, be very cognizant of your units. Times 10 to the minus 4 molarity over second equal to is going to be divided by this product, 0.160 molar times 0.017 molar. And molar cancels out here. So let me write that again so that the units are not, this molar gets canceled. So 2.2 times 10 to the minus 4 divided by the product of 0.160 times 0.0170. You close the parentheses, hit the equal sign. Our units are going to be seconds to the minus 1, or inverse seconds. And that product, when I put it in my calculator, I get an answer of 0.809 with 3 sig figs. Even though this is 2 sig figs, I'll go with 3 sig figs here. A final rate law, a final answer in all of this, is the rate for this reaction. Answer in all of this, the rate for this reaction is rate is equal to 0.0808 seconds. Concentration of S2O8 raised to the first power times I minus raised to the first power. This is your final answer. The rate constant times the reactant raised to its order times the second reactant raised to its order. This equation actually relates the temperature to the rate constant, And the temperature is on the x-axis. The rate constant K is on the y-axis. Remember, the rate constant K will have different units dependent upon whether that rate and its reactants go by 0, first, or second order decay. And so as you increase the temperature, the rate constant actually increases. So we have to quote a specific rate constant K at a specific temperature. K gets specific temp T, and here is the Arrhenius equation. We can do a transformation of this, and essentially we get this term here. Natural log of the rate constant is equal to the activation energy EA. Now the activation energy is the energy required to overcome for the reactants to form a transition state, and once they form that transition state, they can go back and form the products C plus D, or whatever the products may be. So the activation energy is that initial hump, and that's related to how the reactants orient towards one another. It's related to a many different number of factors, but obviously if you increase the temperature, you're increasing orientation, you're increasing a whole host of factors that favor the transition state as the molecules increase in motion and degrees of freedom. So that activation energy is divided by R times 1 over T plus the natural log of A. A is the frequency factor. That's sort of a constant, and that constant is related to how much the collisions are productive. So when you make a transition state intermediate, the orientations of the reactants must be right. They must be productive collisions. So the frequency factor takes into account what are known as productive collisions between the reactants, say A and B. Between A and B are not productive, then transition state won't release products. Relationship between determining the rate constant at a quoted temperature, just as similar to the Clausius-Clapeyron equation, where we quote a particular vapor pressure at a temperature T. So instead of K1 rate constant at T1 temperature and K2 rate constant at temperature T2, remember the Clausius-Clapeyron equation was vapor pressure P1, pressure at some temperature T1, and that was the heat addition over R, and this was vapor pressure 1 at T1 minus vapor pressure 2 at T2, div 1 over T2. So notice the overlap in terms of the graphs, and the overlap in terms of the equation. So there's a lot of similarity in determining the rate constant relative temperature at which it's quoted at. Same holds true with the vapor pressure and the temperature at which it is quoted at. Notice also what binds together the rate constant with its temperature is the activation energy. And what binds together a vapor pressure with its temperature is the delta H of vaporization. Our practice problem utilizing the Arrhenius equation. The Arrhenius equation will be used a little bit differently in your lab, so I suggest you look at the point notes that are attached on Blackboard for a different variation on how to solve for the Arrhenius equation. First order rate constant for methyl chloride with water to produce methanol and hydrochloric acid is this. We're told that it's a first order rate constant, so these reactants are going to overall order is going to diminish with first order kinetics. Calculate the rate constant at 40 degrees if the activation energy is 116 kilojoules per mole. So in this particular regard, we're going to have to convert our temperature to Kelvin just because our units of R is 8.314 joules per mole Kelvin. K1 here, 0.32 times 10 to the minus 10, that's a really small number, at 25 degrees. So that's my K1 and T1. So K1 will be 3.32 times 10 to the minus 10. I'm not going to put any units in my log because natural logs inside, no units gets put in there. And so that is going to be at 25 degrees C. My activation energy here is 116 kilojoules per mole. I'll make that 116,000 joules per mole. 8.314 mole Kelvin. We have 1 over T2. T to be 40 degrees C. I'm going to convert that to Kelvin, and that's going to be 313 Kelvin. T1, which is 25 degrees C, which is the same thing as 298 Kelvin. I'm just going to solve for K2. I'm going to do all of this math first, messy math, and I'll put that in my calculator. Minus 2.244. Moles cancel, my Kelvin cancel, my joules cancel. That's good because usually you don't want to have units inside that natural log. And all of this has to equal to the natural log of 3.32 times 10 to the minus 10 divided by K2. So let's take E of both sides of the equation. So I'm here. On both sides, that's the inverse natural log. To the power of natural log of 3.32 times 10 to the minus 10 divided K2. Fraction is by the natural log, and we take the e to the power of all of that, and that has to equal to e to the power of minus 2.244. So e to the natural log of x is just going to equal x, so this pops that out. So 3.32 times 10 to the minus 10 over K2 has to equal to this. On my calculator, when I take e to the minus 2.244, 106, I'll put an extra digit here, 0, put maybe another one, 106.03, I'll just carry that so that I can get a little bit of extra accuracy in my calculation. So let's solve for K2 here. K2 is going to equal to 3.32 times 10 to the minus 10 divided by 0.10603, and when I do that, I get a value of 3.13 times 10 to the minus 9. Let me be cognizant of my units. My units for my rate constant as quoted here are seconds to the minus 1. That is to be expected for a first order rate constant. So my units for this rate constant at this temperature, at that temperature, my rate constant is 3.13 times 10 to the minus 9. Degrees, my rate constant, or how fast the reaction proceeds, that constant is 10 to the minus 10. I raised it from 25 degrees to 40 degrees, and my rate constant increases by an order of magnitude. 3.13 times 10 to the minus 9 is 10 times faster, higher temperature than 3.3 times 10 to the minus 10. So again, increase the temperature, increase the constant. And the rate constant is really directly proportional to the temperature. Raise the temperature, increase the rate constant, and henceforth increase the rate of the reaction.